Thanks for the introduction, and also thanks to everyone who staying here for the last session. And it's my first time attending AutoCarto conference, and I'm so impressed by the high quality presentations and the event organization. Everything is so awesome. I just want to express my thanks to everybody who contribute to this fabulous event. Today, I'm going to introduce our project that aims to solve the scale issue in spatial temporal modeling. The project includes several components, including the triangle model for temporal analysis, the pyramid model for spatial analysis, and the higher dimensional framework for spatial and temporal analysis. I'll start the story from the triangle model, which is a two-dimensional representation of time. Conventionally, time intervals are represented as linear segments in a one-dimensional space. The linear time is intuitive to many people. However, it may not be efficient for data visualization and analytics. Alternatively, a time interval can be projected to a point in a two-dimensional space using the midpoint and length of the interval as coordinates. The position of the points carry all information of the time interval as described by the linear model, but more efficiently. In such a way, a large number of time intervals can be projected to a point set in a fixed coordinate in a two-dimensional space, which can be easier for visual analysis and the pattern detection. In addition to discrete time intervals, time series can be represented as continuous field in the triangle model. In the triangle model, statistics in different lengths of intervals are calculated in different lengths of intervals are displayed in a single view. From the higher level of the triangle, you can see the general trend, while from the lower level of the triangle, you can see the short-term fluctuations. And most importantly, you can see the nested relations between the short-term and long-term patterns. We have developed many analytic tools to, based on the triangle model, to analyze archaeological data, mobility data, and even sports data. And you can find most of these applications in the review paper that I listed on the bottom of the slide. In addition to temporal information, we apply the triangle model to analyze linear features in a geographic space. Distance is the fundamental spatial metric that has been widely used to do spatial analysis and modeling. However, how to measure distance in a 3D terrain is not a simple question. The measurement uncertainty is dependent on the resolution of the DEM, the terrain type, and also the surface adjusted method. So to answer this question, we evaluate the performance of 7 distance measurement methods listed here in different situations. So we create a random transect in a 3D digital terrain, and then we measure distance in fixed intervals along a transect, through a transect, and then compare the distance measurement with the benchmark distance. This line chart shows the measurement residual of the 7 measurement methods in 9-meter intervals along the highlighted transect, where it shows that the weighted average method generally has the lowest residual, means it is most accurate in most of the intervals. However, if we compare the method in longer intervals, say 50 meter, 100 meter, the results are different. If we want to do that comparison, we need to create other line chart in other distances. Alternatively, we can represent the measurement residual measured in different lengths of the intervals in the triangle model. And then we create triangle model for each of the 7 methods. The triangle model are essentially continuous surface that can be represented in two-dimensional raster data. So we can use raster overlay to compare the residuals in the different triangles. The output of the raster overlay can display the optimal measurement method in all lengths of the intervals. With the optimal method means the method that has the least residual. This allows us to compare the 7 methods in additional dimension. That is the resolution that we use to measure the distances. So here, this triangle model shows that in the 10-meter resolution DEM, the weighted average generally has the highest accuracy in almost all intervals, except the very short intervals on the bottom of the triangle, where other methods could be more accurate. However, if we look at the comparison in digital elevation models in other resolutions, for example, in the 500-meter resolution, the bilinear methods outperform all other methods in longer distance intervals, while in some short intervals, the biquadratic and the weighted average may be better. In the 100-meter resolution DM, the bilinear method and the weighted average method are two competing methods in different lengths of the intervals. In addition to triangle model for temporal data, we can extend the same modeling principle to the pyramid model for multi-scale spatial data analysis. The concept of the pyramid model is very similar to image pyramid that has been widely used for multi-scale image storage and the rendering, but the analytic power of this model has not been fully explored. The pyramid model represents spatial units in different sizes in a 3D point lattice in a 3-dimensional space, where each point represents a spatial unit. The horizontal location of the point represents location of the spatial unit, while the height of the point represents the size of the spatial unit or the extent of neighborhood around that unit. Taken raster data as the example, the finest spatial units in a raster data are pixels, which are represented as points at the finest resolution. Well, then the points at the second level represent focal windows of 2 by 2 pixels, and the points at the nth level represent focal windows of n by n pixels. In such a way, focal windows of different sizes are represented in a 3D lattice, creating a multi-scale structure of spatial data. In addition to raster data, the pyramid model is also applicable to other spatial tessellations, such as polygons or other shapes of tessellations, and also for spatial indices calculated in different neighborhood and bandwidth. Next, I'm going to show some applications of the pyramid model. Quadrant density and the kernel density are the most common method to analyze point patterns. However, both methods suffer from the same issue. We need to find the appropriate quadrant size or kernel bandwidth to calculate the density. However, in triangle model, it can resolve this issue by representing the density calculated in different quadrant sizes and the kernel bandwidth in a multi-scale structure in the pyramid framework. Well, different from conventional quadrant analysis that is calculated in a fixed grid, here the quadrant analysis are calculated within focal windows rolling through the point set. The quadrant density calculated in one size of focal window are represented as one layer in the pyramid model. Then this process repeats for different sizes of quadrant windows, creating a 3D volume where each voxel represents a specific size of focal window and is associated with the density calculated in that specific focal window. And using the pyramid model framework, we can visualize the global density peak of quadrant density calculated in different sizes of focal windows. The global density peak means the point that has the highest point density calculated in a specific size of focal window. Linking the global density peaks calculated at different scales, we can create a line stream showing in these two figures. The line stream displays the continuous movement of the global density peaks calculated at different scales. And it's important to note that the shift of the global density peak and the magnitude of the shift are readily apparent in the pyramid framework that might be difficult to identify in selective or single-scale analysis. In addition to global density peak, we can also use isosurface to select and display voxels where the density is above a certain threshold. So here, the visualization, this voxels shows the focal windows where point density is in the 99th percentile. In other words, these voxels represent point densities that can be detected in different scales. And while the 3D visualization gives us a view of the hierarchical structure of the multi-scale point pattern, where you can observe subtle voxels at the lower level of the triangle representing local points clusters that can be only detected at the fine spatial scale, and general clusters that can be detected at the larger scales, and most importantly, the hierarchical structures between the multi-scale patterns. And the most important feature is that we can detect some voxels that floating in the middle height. These voxels are particularly interesting because they represent some point clusters that can only be detected in specific range, but they are not visible if the scale is too fine or too coarse. In other words, these are the spatial patterns that are often neglected in single scale analysis or selective scale analysis. We can also use the pyramid model to visualize a global density peak for kernel density. In general, the line stream shows how the location of the global density peak of kernel density shifts its position when the scale becomes coarser, and the magnitude of the shift is generally lower than that of the quadrant density, but they generally follow the same trend. The local density peaks represent local maximas, which means location where the point density is higher than its neighborhood positions. And the local density peak visualization shows how the point patterns emerge from fine spatial resolution and shift its position, dilute, and converge with other clusters when the scale becomes coarser. The isosurface of kernel density can display the extension of point patterns along the scale dimension. So here, on the bottom of the triangle, the short cylinders, or more look like bamboo shoots, represent local clusters that are only existing at very fine spatial scale. And the long, large cylinders represent general clusters that extend from fine spatial scale into a larger scale. And most importantly, we can observe how the local clusters converge into general clusters when the scale becomes coarser. So point pattern analysis is one application of the pyramid model. We also apply this model to analyze land cover change. Well, due to the time, for the sake of the time, I'll go through this part quickly. Thanks. Well, as the most vulnerable coast in the United States, Mississippi Delta suffered from tremendous amount of land loss. However, although the causes of the land loss can be complicated and multifaceted, but many literature point out that land fragmentation is a major driver for land loss in this region. If we look at the zoom-in view, we can see the aqua farms, man-made canals has cut the coastal wetland into small pieces, which accelerate the wetland loss. So to understand the relation between land fragmentation and wetland loss, we represent a fractal dimension calculated in different sizes of focal windows, and the land loss ratio calculated in different sizes of focal windows in pyramid models. Using the 3D visualization, we can analyze the variation of the two indices in space and across scales. And most importantly, we can analyze the relation between the two indices in the multi-scale framework. For example, we can conduct analysis, regression analysis. So these two figures shows the adjusted R-square and the coefficient B at different scales between land loss ratio and land fragmentation, which give us clues at which scale range the relation between the two indices are prominent, and whether the relation is positive or negative. And in the next step, we are trying to conduct local regression analysis in the pyramid model framework and analyze how the regression coefficient varies not only in scale, but also in different locations. And this is an ongoing project. I would like to express my thanks to a very excellent research team formed by researchers from 3 institutions. And I'm happy to take questions. Thank you very much for your attention.
Thanks, Yi. Do we have any questions?
I have one question. Thanks for your very interesting research and your very detailed presentation. Because I saw your research have considered the multi-scale of spatial pattern. Have you considered the multi-scale of temporal pattern to your research?
Okay, that's a very good question. And this is also part of our project. We created the triangle model, which is a multi-scale representation of temporal data or linear data, and a pyramid model for spatial data. And I haven't got time to introduce a higher dimensional framework that actually include the 5 dimensions: spatial location, temporal location, spatial scale, and temporal scale. And it's difficult to visualize the high dimensional framework in any 3D or even 4D animations, but we are trying to develop, use either linked views or use statistic models, trying to identify some patterns, not only in multiple spatial scale, but also multiple temporal scale. One of the applications is detecting climate anomaly. So this is really dependent on location, time, spatial scale, and temporal scale. So how to consider all the different factors and detect what is called climate anomaly, extreme heat, how to define extreme heat in what extent, spatial extent, in which time interval. That's something that could be solved by the higher dimensional framework. Thank you for your question.
Great question, thanks. Others? Okay, I think we'll go ahead and move along for time's sake. If you have any other questions, you can ask afterwards. Thank you.